Hello and welcome back to Calculus 3, section 16.1 on 16.2. Double integrals over general regions. The first lesson was rectangular region, meaning the domain was a rectangle. Now we're going to have any shape in the domain, and that will be bounded, let's say, by two functions. So 16.1, domain was a rectangle. 16.2, domain might be a function, let's say g, and a function h. So you have this versus what used to be the rectangle before. So that's the only difference. That's the only difference. However, that difference turns out to be a big deal when you start writing functions and calculating things. In 16.2, our integral now becomes volume equals double integral of some function xy dA, and what you have here, well, actually not dA, dy dx, and what you have here are a and b for the x, but you have some function h of x and g of x in the limits, or double integral f of xy dx dy. You have a c and d now to correspond to our dy, and h of y, g of y to correspond to dx. So this is the new setup, and our region is no longer a rectangle. So I'm going to pick, can call them number 1 and number 2. It's just dy dx or dx dy. So I'm going to pick the number 1 to explain certain things, and then we just need to do problems. First off, the two integrals inside are linked, and the integrals on the outside are linked. When you're setting these integrals up, the outer integral must be with numbers as limits, because you are going to get a number as an answer. So numerical values now, don't get confused that this is dy and you have h of x. If you have a dy integral, then these better be y1 and y2. Now, if you remember your pre-calculus, y is a function of x. So it's okay to have h of x here, because h of x is y. H of x is y. G of x is y. So these limits to be h of x and g of x, that's perfectly fine. That's exactly what we need. the inner integral functions. You have y is h of x and y is g of x. So now if I am to draw this x, y, and z, let's take a look at some kind of situation here. So say you have some kind of a parabola in a domain, and that parabola is intersected with a straight line here and here, creating region R. And then you will have some top that is there. Immediately, you draw this in a domain separately so that you can see what is happening. So what I have is x-axis, so I have a parabola that does this, going through some value on y. Let's say that value is 4, let's say. And then the x-axis, we have a line that goes through the origin, like so, and that cuts this region over which you have the rest of the cookie, because the region is the cookie cutter, right? The black lines outlining this region is the cookie cutter, and the red, what is shaded there, is the bottom of the cookie, whatever is touching the table or the plate, whatever. So the cookie is built on top of that red, in the case of the board coming out of the board. So now I have the standard calculus 2 area between two curves. You have the top function g of x, which is the parabola, and the bottom function h of x, which is the straight line. Further, these intersect here and here. Those intersections give you A and B. So now when I set up my integral of whatever unknown function we have, dy dx, I have my A and B, and I have my red upper function g, lower function h. Now I like to observe the representative rectangle, so draw somewhere representative rectangle dx, and with a single representative rectangle you can set up both integrals with their limits. So whatever is the outer integral, that's the representative rectangle you draw, and the rest is a joke. Look, dx, the outer integral, it's going to go, the limits for x are going to be from a to b, because that dx moves from left to right. So from a to b on the outer integral for dx. And the top and the bottom of that dx always write the same functions. The top writes g of x, and that's on top of dx. And then the bottom writes on the function h of x, which is the bottom. So the same idea with the dx that you guys used to set up the area between two curves. Now you will use the same thing to set up area of the between two curves area for the domain, and then you are integrating f of xy. Now, if you haven't realized yet, if I am to remove this f of xy, this is just the Calculus 2 formula for area between two curves. Because when you integrate dy, all you're going to get is g minus h. Well, wasn't that f minus g? You called it f minus g earlier in Calc 2. Now, I'm just calling it g minus h because the f was taken for something else. So this formula collapses down to area between two curves if you remove this third dimension, which is the z dimension. It stops being a volume, it becomes the area because you removed z. Once you remove z, then you just have x times y. And it quickly becomes the area between two curves. So let's take a look at an example of this. See what they have. Okay. First, skill. Problem 13 is asking you to compute double integral on xy dy dx 0 to 2 and x squared to 2x. Well, the inner integral is in terms of y. So copy the outer one, 0 to 2. The integral in terms of y becomes y squared over 2. We copy x because that's constant. And now you'll get to plug in the limits that are x squared and 2x inside the y. So this is 0 to 2, copy x, and now this becomes 4x squared over 2 minus x to the 4 over 2. Because 2x squared, right, you're plugging into y, 2x squared is 4x squared, and then x squared squared is x to the 4th. Now you clear this algebra, 0 to 2, that's 2x cubed minus 1/2 x to the 4th dx, and now you integrate that. That's going to be 2x to the 4th over 4, so x to the 4 over 2, minus 1 over 10 x to the 5 from 0 to 2. We don't have to worry about about 0. It's a polynomial. So 16 over 2 is 8, minus 32 over 10. Well, that's just 3.2, so 8 minus 3.2 is 4.8. Done deal. Calculation is the same, except this time around, you get to plug in functions, not numbers, and shovel algebra. So computing this, again, you go in the inner integral first, solve all the way, then the outer integral, solve all the way. And if you follow that these must be numbers at the end, you will get a number at the end. If you have these as functions, then clearly the answer must be in terms of whatever variables you had on the outside. So you should always stick with having the numbers on the outside. Let's try another example. Okay, so this is now problem 44. You are supposed to integrate over region R, x plus y dA, where R is a region bounded by x equals 0, y equal x squared, and y equal 8 minus x squared. All right, try that. Yeah, no pressure. 18 seconds. Go.
It's all in 18 seconds. Definitely should not be sitting here in orbit. Yeah, should be that late.
Greatest of integral.
Right now you can do just sign up to the online reserve list. Yeah, the one that's right now, there's like a lot of problems with this.
I'll set this up.
You have to charge, you have to hold it open. Right. There's a good bad feature though. But the change, it's a plus. Like, this guy did a whole breakdown. I mean, Razor's coming out. The Razor too. Yeah, it's actually coming out. But it's like the same as a Razor, but it's only all touch.
So that's really
That's
So I'm saying like, why can that be like, one of those multiple flip?
yeah, that's the Razor. You know what I'm talking about? No, he's saying why Samsung doesn't. Oh, no, they were, well, it's Samsung.
Yeah, plus X.
Well, they had that. Well, they had that, they had the sidekick coming up too.
I had like this.
I
I think I know what to
I don't
do.
know if it's called the Razor 2, but the Razor phone, I think it's LG, the original flip phone, one of the, this is back in my.
Okay. So, as always, the first thing you have to do without thinking is to draw the domain. Nothing can be done here without the domain. because domain will tell you what to put in limits. We have, well, x equals 0 is the y-axis. Then we have x squared, that's a parabola that opens up. Then we have 8 minus x squared, it's a parabola that opens down. And x0. So, seems that we are bounded on one of the two sides. So now I'm going to draw the representative rectangle delta x. And we are ready to set this volume. We are integrating x plus y. And now, because we drew dx, we have to put dy dx. Whatever we draw, that fits. You do not want dy here, like that, because dy will ride two different functions on the right side and the y-axis on the left. That's not good, right? We want, preferably, everything in one integral. So dx is always going to ride x squared on the bottom and 8 minus x squared on the top. And it's going to go from 0 on the left to whatever this value here, this b value is. And that we have to find when we equal the two functions. So 2x squared is equal to 8, x squared is equal to 4, x equals plus minus 2. Now we just need a positive 2, obviously, because we are only on the right-hand side. So pretty much the same as the area between two curves you guys dealt with in your Calculus 2 lecture the first day. And now we just need to integrate. Integral 0 to 2, integrating in respect to y, so we get xy plus 1/2 y squared from x squared to 8 minus x squared dx. You have to be careful with all of these now limits and substitutions. So we're going to have, instead of y, 8 minus x squared. So it's x times 8 minus x squared plus 1/2 8 minus x squared squared minus x times x squared minus 1/2 x squared squared, all of that dx. Integral 0 to 2, and now we just have to multiply everything. So this is 8x minus x cubed plus, we have to FOIL this and apply a half. That's a 64, half of 64 is 32, so 32 minus 8x squared plus 1/2 x to the 4th minus x cubed minus 1/2 x to the 4th dx. Oh, that's great, these cancel. And what do we get? 0 to 2. X cubed is the highest exponent, so that's negative 2x cubed. Minus 8x squared plus 8x plus 32 dx. And now we are back in Calc 1. So negative 2/4, that's negative half, x to the 4 minus 8/3 x cubed plus 4x squared plus 32x from 0 to 2. That's 16 by negative 8 minus 64 over 3 plus 16 plus 64. minus 0, 0, 0. That's all good. That's an 8 minus 128 over 3, because 64, that's 3 of those, minus 1 of those is 2 times 60, yep. 3 times 8 is 24, so negative 104 divided by 3. So if all calculations went well, negative 104, I don't like it, but that's what I have. If all calculations went well, I don't like it's negative, it's volume. But it's way too many numbers to fix. Now, these guys, I think, you can work out these in Mathematica as well. So try typing in a double integral and see what you get, especially you need it for your lab as well. Yes?
Why is that having found like x plus minus 2 but we're not going to just positive?
Because the picture is cutting it off at x equals 0.
Okay. Oh, okay.
So it cuts the y-axis, cuts. Yeah, you do have a negative 2. Negative 2 is the other side.
Yeah.
But the other side is not shaded red because x equals 0 cuts, just use the first quadrant. Yes?
Yeah.
When I combine, oh, it's a positive. 64, that's a 64 plus 64 plus 64 over 3. Well, 3 times 64, and then you take 1 away from here. Yes, so that's a plus there. Well, thank you. 24, that's 152, right? 152. This is negative 64 plus 3 times 64 over 3. So that's 2 times 64, 128. Yep, all right. And then 128 plus 24, 152. Good catch. Nice. Nice. Changing the order of integration. Now this is a biggie. You can't just swap. If you swap, then the outer integral, which was all numbers, that was going to go in, you're going to get variables in the end, and it's just not going to work out the same. So you cannot just swap. Nice one. Is it possible to interchange order? Yes. But it's a process. So here is the problem 64, and we'll do more after the exam. So now you might, I started talking about this last lecture, and then I realized that it's better to do it here. I can't integrate this. I need at least a y in front of sine so that I can use u sub. And I don't have it. So it cannot be integrated And if you want to, force it, then go ahead, use the power series, right? And get the approximation from Calc 2. But to integrate it exactly, it can't be done because you have sine of y squared. So the only option here is to hope that if you are to swap the order of integration from dy dx to dx dy, that it will work out differently so that you can work this in some sense. So let's first realize a few things. I have a domain that it's purely given by these two. So I get to draw the domain looking at these only. What do I have from here? I have that x1 is equal to 0 and x2 is equal to pi. That's what I get from the outer integral because the outer is the dx. So x equals and x equals. The inner one is y equals and y equals. So y1 equals x and y2 equals pi. And all I need to do is to draw these four on a single graph over here and shade the region. I already know that my f of xy is sine y squared. I know that. That's given. The only function here is y equals x. So I'll draw the 45-degree line through the origin. Right, that's y equals x. And now I can choose pi, let's say 3 squares is a pi. So I have y equals pi. I have the y equals x. I have x equals 0. And x equals pi. So we are talking about this triangle here. Because this triangle is the one that is stuck in between the functions that are given to us in limits. Here is your x equals 0. Here is your y equal pi. Here is your y equal x. And this point, single point here, is x equals pi. Because it's all the way to the right. Now, some of you might say, well, why don't you just drop a line right there? That's a line, x equal pi, and then shade below. No, because I don't have this line, which is y equals 0. That line was not mentioned anywhere. And that's why I don't get to shade the bottom region. A lot of mistakes on exams by picking up the wrong region. It is very important to learn how to transform the region into limits and then limits into regions. Clearly, all of this gets more convoluted when you get into 3D with the triple integrals. So right now you only have two integrals to worry about. And if you follow the prescription that I show over here, where you go to the first integral and say first integral is x equals and x equals, because you learn in Calculus 1, a, b, f of x, dx, and they say this is x1 lower limit, this is x2 upper limit. So we say x, 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 right there, all x's across the board. They all have to match. You cannot have y anywhere. They all have to match. That's what we learned in Calc 1. So now, in Calc 2, you just have two of those. If this is an x over here, then this is x1, this is x2. They all have to match. All right. So now that I have this, and it was given as dy dx, I'm going to now work this as a dy rectangle. And put these limits so that I have my sine y squared as dx dy. Okay. My y limits on the outside are 0 to pi, because the lowest this dy can be on the floor, on the bottom, is at 0. And the highest it can go is y equals to pi, to hit the ceiling, right, of the shaded triangle. Now, we clearly see that the y-axis is the limit to the left, so we have a 0 there. And then it extends to the right to hit the line, but guys, this is the inner integral x, so this has to be x equals y. So this is a y now. That's a y. And now we integrate in respect to x first. So integral of this in respect to x is going to be x sine y squared, calculated from 0 to y, and we still have dy. And then we have integral 0 to pi, plug in y sine y squared, and there it is. Now we can use u sub to solve this. Minus 0, because when it kills it. And now we can use basic u sub. Y squared, du is 2y dy. I need a 2.5 in front. Becomes 1/2 integral of sine u du, and the new limits are 0 and pi squared. The integral of sine is negative cosine, so negative cosine of u, there's another half in front, so negative half cosine u, 0 to pi squared, which gives us negative 1/2 cosine pi squared. And that's a number. You can, punch this in the calculator if you care and get the values. Maybe right here, negative 1/2 cosine pi squared, and get rid of this. Save the digital paper. All right, let's recap this. This was the change of variables. As you can see, not just a swap like in a previous lecture. What we do over here is we realize that we cannot integrate because sine y squared dy cannot be integrated. We swap x's and y's. And when you swap x's and y's, well, in order to do the order of integration, change in order of integration, you have to draw the domain. And domain is encoded here in the limits. So you just read it backwards as the numbers. If this is a y, then those are y numbers. If that's x, then x numbers. And the same goes from the middle. Once you draw the functions that are involved, you shade the region, right? Because it will, that region would be completely bounded by those 4 different values you have over there, whether they're numbers or functions. And whatever is completely enclosed by those, that's your region R. And then you can read that region the other way. Let's do one more of these. And that's it. Let's see. Well, 66 is fine. I mean, it's terrible, but it's fine. 0 to 4, square root of x to 2, x raised to y to the 5 plus 1, dy dx. Can't integrate because I'm supposed to integrate in terms of y. I have y to the 5 in the denominator. I need to be able to fix this somehow. What are all the configurations that I actually can do? You see, if you know what you can do, then it's easier to spot what you can't do, right? So you would be able to integrate x over y plus 1, because that would be a basic u sub and just would work out to be ln. Great, so that one is easy. X over y squared plus 1. Well, that one will work out to be inverse tangent. So that one is easy as well. And finally, if you had some form of y to the 4th x over y to the 5 plus 1, that one would be also easy because that one would be basic u sub. So going from, exponents on y in the denominator, they should be either 1 or 2, or if you want to have a 5, you better have y to the 4th in the numerator, and in that case, this integral would be easy, and we wouldn't have to mess with any of the other work. However, we have y to the 5 without y to the 4th, and we cannot integrate at all. You cannot integrate this at all. So if the changing of the order doesn't work, well, then it would have to be some power series or some other approximation method, because you can't integrate at that point. So what do we do here? Well, we extract again all of the information. Number 1, x1 bottom limit is 0, x2 upper limit is 4. Function y1 is root x, function y2 is 2. We have that f of xy is x over y to the 5 plus 1. So these are our parts here. Now we're going to draw the domain. You have the 4 functions. Step number 1 always is draw the domain, so you know what you're dealing with. These problems can't be solved in any other way, so you have to do this. The only function out of the 4 of these is a square root function, and you know what that looks like, so there we go. X equals 0, x equal 1, 2, 3, 4. Y equal to 2. And my question now is, do I shade the upper part over here or the bottom part over here? Why would it be upper and not the bottom part? Very good. It's between square root of x and 2, and that's the top part. This would over here need to be a 0, guys, to have the bottom part. It's the dx stretches between these two, and that's here. The other one would be 0 to root 2. So you have to be very careful which one you pick. Excellent. So now we have this. And I need to draw my horizontal, in this case, representative rectangle dy. And now we write a double integral for the function x over y to the 5 plus 1. And we need this one to be, it used to be dy dx, now it's going to be dx dy. Okay, so y goes on the bottom, 0, all the way to the top, which is 2, as it swipes from bottom up, from 0 to 2. The left-hand side is always touching dy, so that's a 0. And the right-hand side is touching what function? It's touching the function y equals root x. But I can't have it as y equals. I need it as x equals function of y, which means you need to flip this. When you square both sides, you get x equals y squared. So this one becomes a y squared. You have to flip the function. You dealt with this flipping of the functions many times in Calc 2 to deal with the dy integrals, right? So you know to flip it x. I mean, you know how to change this. And now we just integrate. Well, I'm integrating the inner integral in respect to x. Well, isn't that a joke? I'm just integrating x. That's x squared over 2. The whole denominator is a constant because it only contains y's. So the first integral, which is the inner integral, is simply going to be x squared over 2, everything divided by y to the 5 plus 1, computed from 0 to y squared, and I still have dy to deal with. I can kick 1/2 in front of the integral, and y squared squared is y to the 4th over y to the 5 plus 1 dy yoo-hoo. Basic u sub. U equals y to the 5 plus 1. Du equals y to the 5 y to the 4. 5 y to the 4 dy. I don't have a 5, so I'll have to put a 5 and 1 over 5 in front, which makes it 1 over 10 now. Integral of, and what do I get? I get du over u. And what are my limits? When I plug in 0, the bottom limit becomes 1. When I plug in 2, so 3 is 8, 16, 32, 33. You have to plug in 0 here. You get the bottom limit 1, and then you plug in 2 over here. So that's 32 plus 1 is 33. Change the limits. 1 over 10. ln of u, computed from 1 to 33. Now ln of 1 is 0. So 1 over 10 ln of 33. Tons of fun. So I'll just write here just in case. We must use domain to change order of integration. Cannot simply swap. That works only in 16.1, the previous section. So the double integrals, to sum both of these sections, double integrals can be used to find the volume over some kind of two-dimensional domain. 16.1 rectangles and 16.2 pretty much everything else. You find the volume when you have the shape built on top of that domain. If you remove a function from the double integral, it collapses down to the integral for area between two curves, because once you remove the function from the integral, that f of xy, you are effectively removing the dimension z, and the only two dimensions that are left in the game are x and y, which means that the whole integral collapses down to area. So whether you have 16.1 or 16.2, we don't care. We have that the volume is equal to double integral over some region of f of xy dA. That's 3D. Or you can calculate area over the region dA if you are not using f of x f of xy, right? Because in that case, you just have delta x times delta y, which is the area. And that collapses to area between two curves, right? Because you have the f of g minus f of h. So that's the integration. After the exam tomorrow, we are going to take a look at the after the exam, we're going to take a look at the double integrals for polar coordinates, which would be the last one on double integrals. And then Wednesday is reserved for triple integration. We have rectangular, general, cylindrical, and spherical. And then center of mass and changing the U substitution. Technically, it's a UV sub, multivariable substitution for multiple integration. Next week we have sections on vector fields, and the course is over. I get to see you another 7 times. That's it.